The paper of the day is Paxos Made Simple. The Paxos algorithm for implementing a fault-tolerant distributed system has been regarded as difficult to understand, perhaps because the original presentation was Greek to many readers. In fact, it is among the simplest and most obvious of distributed algorithms. At its heart is the consensus algorithm, the synod algorithm of the part-time parliament. The structure of the paper is familiar. First, Lamport explains the core consensus protocol that enables a set of participants to agree on a value between them. Then he shows how a distributed system can be implemented that keeps a set of servers in lockstep by running an instance of the consensus protocol for each decision they take. At the core of the consensus algorithm is a simple fact that it might be worth dwelling on first. Imagine a set of coins that have all been tossed and are now lying flat on the first surface of your table. If a majority of those coins now show heads, then it is impossible for there to be a majority that show tails at the same time. We can generalize this to any set S with members free to choose from value V. If the majority of the members choose from some value V, then it is impossible for there to be a majority agreeing on any value other than V. Now let the members of S each choose a new value and suppose that a majority choose some new value V prime. At least one of the members in the new majority must have been a member of the earlier majority. This follows straightforwardly from the definition of majority. If you subtract from S the set of members in the original majority, there are by definition not enough members left from a majority. Therefore, any new majority that does form must do so by including a member from a previous majority. Looking at the consensus algorithm, assume a collection of processes that can propose values. A consensus algorithm ensures that a single one among the proposed value is chosen. If no value is proposed, then no value should be chosen. If a value has been chosen, then the process should be able to learn the chosen value. The safety requirements for consensus are only a value that has been proposed may be chosen, only a single value is chosen, and a process never learns that a value has been chosen unless it has actually been. An asynchronous non-Byzantine communications model is assumed. There are three roles to be played in the consensus algorithm: proposer, acceptor, and learner. A single process may play multiple roles. A proposal to agree on some value consists of a proposal number and the candidate value. Each proposal has a distinct proposal number, but more than one proposal can propose the same value. Agreeing to accept a proposal requires a majority of acceptors. As we saw earlier, it is impossible to form a subsequent majority without including at least one of the acceptors from an earlier majority. There is a very clear derivation of the core consensus protocol that shows step by step why it needs to be as it is. An outcome of this chain of reasoning is a constraint on the proposal number and the proposal value that a proposal may put forward in any new proposal before issuing a proposal with a proposal number. N, a proposer must ask a majority of the acceptors for the proposal value of the highest number proposal. Learning about proposals already accepted is easy enough. Predicting future acceptance is hard. Instead of trying to predict the future, the proposer controls it by extracting a promise that there won't be any such acceptances. In other words, the proposal requests that the acceptors not accept any more proposals numbers less than n. Now, there's a two-phase protocol. Let's look at the prepare phase. A proposer selects a proposal number n and sends a prepare request with the number n to a majority of the acceptors. If I make a proposal with number n, are there any constraints on the value I must propose? If an acceptor receives a prepare request with number n, where n is the greater than any of the prepare requests it has already responded to, then it responds with the promise not to accept any more proposals numbered less than n. And that is the highest number of proposals that it has accepted. Acceptors therefore need to maintain as reliable state the highest number proposal they have accepted and the high watermark value of the largest n it has responded in a prepare request. This diagram shows the prepare phase. Take a minute to appreciate it. Accept phase. Precondition. A proposer has received promised responses to its prepare request number n from a majority of acceptors. The proposer sends an accept message from proposal NV, where V is the proposal value of the highest number accepted proposal amongst the promises responses and any value the proposer chooses if no prior acceptance has returned. If an acceptor receives an accept message for a proposal number n, it accepts the proposal unless it has already responded to a prepare request with a higher value than n. Here's the diagram depicting the accept phase. Pause the video and take a moment to appreciate the diagram. Learners. We said that there are three roles: proposer, acceptor, and learner. A learner is someone that needs to discover that the proposal ultimately chosen by the majority of acceptors actually is. Remember that these roles are often combined in a single agent. The obvious algorithm is to have each acceptor, whenever it accepts a proposal, responds to all learners sending them the proposal. This allows learners to find out about the chosen value as soon as possible, but it requires each acceptor to respond to each learner. A number of responses equal to the product of the number of acceptors and the number of learners. A less reliable model, but one that reduces communication, is to have one or more nominated distinguished learners to which acceptors send their acceptance notification and then broadcast to the rest of the learners. Here's a diagram depicting learners. Pause the video and appreciate it. Progress. To guarantee progress, a distinguished proposer may be selected as the only one to try issuing proposals. If the distinguished proposer can communicate successfully with the majority of acceptors, and if it uses a proposal with the number greater than already used, then it will succeed in issuing a proposal that is accepted. By abandoning a proposal and trying again if it learns about some request with a higher proposal number, the distinguished proposer will eventually choose a high enough proposal number. Implementing a distributed state machine. So far, we have looked at a single instance or round of the consensus protocol. This enables a set of participants to agree on a single value. From this building block, we can construct more interesting distributed system. Let the state at a given node in a distributed system be represented by a sequence of values. That is, the node is a state machine. If each value in the sequence was agreed by every node as a result of one round of the Paxos protocol and the sequencing itself is also agreed, then we can model for achieving consistency amongst a set of nodes in the distributed system. Because there are multiple rounds of Paxos protocol, this is sometimes called multi-Paxos.